This is a bijection. So under this bijection, the points of R2 are in one-to-one correspondence with the points on the plane, and hence we can think of R2 being sitting inside R3. And that's why we often draw it in this way, saying this is the X, Y, and Z axis, and we say that this XY plane is actually the copy of R2, sitting inside.
Oh, okay. Okay, sir. And then, sir, so you know when you have a matrix called A, and we assume that it has three vectors, A1, A2, and A3. If A3 is equal to 0, then X3, is it equal to 0 or is X3 free?
I couldn't get your question.
Oh, you know when you have a matrix?
I have a matrix.
Yes, you have a matrix A with vectors A1, A2, and A3.
So what are they? A1, A2, A3 are the columns?
No, they're the vectors within, like the A1 is the column, and A2 is the second column, and A3 is the third column.
Okay. So here is the first column, which is A1. The second column, which is A2, and the third column, which is A3.
A3, yes. Now, if A3 is equal to 0, like A3 is the 0 vector, then when we have X3, is it free or is it equal to 0? When we define it in parametric.
When you're writing this when you're saying that this is the 0 vector, that means this is everything, every entry over here is 0.
Yes.
That's what you're telling me.
Yes, sir.
That's it.
So then when we define the solution as in parametric form, and we say X3 is, do we say X3 is free or do we say X3 is equal to 0?
We will come to it, it's too fast, but having a matrix is one thing and having a solution is another. The matrix and the solution are not connected, right? Solution is something else.
Let's say A is in its reduced echelon form.
Okay, we will come to it. We'll come to it slowly.
Okay, sir.
Okay. So, any questions further?
So I just have one last question.
Yes?
In the definition of a transformation, we say in the definition of a linear transformation, we say that a transformation is linear if TU plus V equals TU plus V for all UV in the domain of T. I'd like to ask, does this also hold in the codomain?
I will do it today, so I hope things will get clear after the end of the lecture.
Okay, sir. Thank you.
Okay. Any other questions? Yeah.
Sorry, dumb question. What's the meaning of bijections again?
Okay. So a function, remember a function is given by giving the domain, the codomain, and the rule, which says where should x go to. Okay? Alright? So injective means or one-to-one. That's also another. So these are all the synonymous things that you might use. But I will always use injective. This means distinct x's are taken to distinct outputs. That means if fx is equal to some such thing like fx prime, then it means x is equal to x prime. Okay? Surjective means surjective or onto. This means that, remember, the moment we have this, we have this subset, which I call the image of F. This is the set of all, this is the set of all Fx. As you vary over your x over A. Okay? So this is the set of all the images. So when image, so this is actually a subset of B. When the image is equal to B, that means everything in B is an image. Okay? That's when it is a surjective. And the third option is bijective. The word bi is often used to mean both. Okay? Bijective, or another word is one-to-one correspondence. What is it? It is injective plus surjective. Okay? That means, what does it mean? It means that every x in every x in the codomain, or say, every y in B has one and only ones, which we often say like, has a unique x in A, such that right? The surjectivity says there exists one x such that y is fx, and injectivity says there cannot be two x's, fx and fx prime being the same, forces x is equal to x prime. So, every point has a unique pre-image. Okay? So, what I often like is this stock diagram. If you keep this stock diagram in your mind, then immediately. So, injective means it's something like this. There might be something which is free. That means the stock. Okay, nothing is empty over here. So all these things are mapped to this. This single element is mapped to this. So at some places it might, many things may go to something. It might be that some unique thing is, okay? And bijective means nothing is left alone. Okay? So if you keep this picture in mind, then you immediately see what is it. Okay? Clear? The stock diagram is very, very informative. Okay. Next. Alright. So we started off with sets and functions. Sets, they were just bags. Okay? In a set, there was no order, there was no repetition, nothing. It is just a bag. There an element is there or is it not there? But then next day we started something like a structure. We understood that just like a set, just the collection of furniture is not enough, right? A bedroom has with it, someone said setting, has along with the furniture a particular arrangement of setting. Okay? A living room has along with the furniture a particular arrangement or a setting. So that Going in any place, you know, oh, this is a bedroom, this is a living room, and so on. That arrangement and setting is well known. So similarly, we had a notion of a vector space which is a set along with some more things. It comes encapsulated. It cannot just as the setting. If you are considering a living room, you don't throw away the setting, the arrangement of the living room out of it, right? Just the furnitures don't make any sense. Similarly, when you are speaking of a vector space, it's not just the set. It's the set plus some more things. What are the space? Okay? This binary operation is commutative, associative. It has an identity. Okay? Which we write as 0. The elements of this set V are often called vectors. The 0 is called the 0 vector. The addition is the addition of vectors. And every vector has a negative. Right? We know by this time that the identity is unique. Since it is associative, the negative is also unique. Alright? So we did all of this last time. So this was one structure. So we have to, that's what I was saying last time. To check for a vector space, you need to first check what is the addition, what is the 0 vector, what's the negative, whether the addition is commutative and associative and so on, right? And then there was this another thing which was this scalar multiplication. And it satisfied all those distributive laws. Okay? So, this was our vector space. So, a vector space is not just this set V, but bundled with all of this. It is bundled with all of this. Okay? Anybody is also having computers? I mean to say, doing computer programming? You know something about object-oriented programming these days? So these are objects. And these things are private to this class. So this is a class. Okay? Vector space is a class. And these are internal of things. Every vector space comes in along with this. Okay? And each example, you instantiate each one of them. That's what you do, right? In each class, you have some internal things, and they instantiate there. Yeah? So that's also another way of looking into it. But let's not. So it comes encapsulated. Now, functions. Functions, we can look upon them as some kind of a transformation of a set, right? Functions transform a set A into another set B. Okay? So, it's a transformation. Now, what will be? So, now vector space comes in with a structure. So, just to carry on with our analogy of living room and bedrooms, we also have these structure preserving maps in our life. So, suppose you have a home and you want to shift. Well, You can have some laborers come and pack all your things and just dump them in your new home. Okay? So your old home was your domain, new home was your codomain, the elements were your furnitures and belongings, and it was just dumped there. So that's a function. But you don't like this, obviously, because you'll have to do that work again. So you hire a packer and a mover who takes your bedroom 1 to your bedroom 1 there, your kitchen to your kitchen there. So the structure of your home is preserved. Okay? So he does all the trouble. He takes everything from your bedroom 1, packs them in one kind of carton, and does it for each one of these rooms, packs them, transforms them to your new home. You tell him this is bedroom 1, takes the bedroom 1 things, unpacks it in bedroom 1 itself. Your kitchen things, okay? So the structure is preserved. So it's a much more careful operation. So obviously it costs you more. Here there is also a cost. You have to be much more careful about this structure preservation. Okay? So we have vector spaces V and W. So we need a function which preserves. We need a function which preserves we want to see what does this preservation mean. Okay? So we want to see what does this preservation mean. So we have to preserve what? We have to preserve these negatives, and we have to preserve the scalar multiplication. Okay? So what does it mean? So that's, what do we mean by preservation of addition? So we have what does it mean? Well, it means, so just look back to the analogy. Your things in your kitchen must go to your kitchen, right? So if you take U and V from V, you add them, you get something in V, alright? Your function f will take it to f of u plus v. Now, you could have, on the other hand, already considered fu and fv here. So you add them in w. Okay? You add them in W, but this is in W also. So preservation would mean that these two things are equal. Right? Sometimes diagrams are very good. Let's see what is going on. What is the whole procedure? So remember, we have the binary operation of V also. Actually, we also have the binary operation on W. Okay? And I'm defining another function. Yes. I have another function which I write as f cross f.
Sorry, sir.
Yes.
Just get back again. If you say that U and V, they are the element of, those are the vectors on a space V. Now you went down and you said f at vector U, f at vector that's V as an element of W. Are you saying that V is a subspace at W?
No, I said that V is a vector space, W is another vector space, and I've taken a function from the vector space, from the set of vectors in V to the set of vectors in W. So, for instance,
then they're not related. Is that what you say? That V and W, because they are all vector spaces, but then which one that falls into another one?
No, I am not saying that they are related. I am just having a function.
Okay.
And I'm trying to explain what is the meaning of preservation of the vector addition.
Okay, I get you.
So
Okay.
So I have the addition already over here. I have the addition over here. I have this function V going to W, right? And I define this function. What is this function doing? So I'm defining this function. This is from V cross V to W cross W. What does it do? It takes a pair, XY, and evaluates the pair at X and Y by the same way. Okay? As simple as this. So, takes the pair XY and returns Fx, Fy. Okay? So now let's see what is happening. So I take a pair U and V from here. This one, so what is happening is, let me do this in another color possibly. So what is happening? So I take a pair. This by my addition goes to U plus V. This F takes this to F of U plus V. Well, as I have defined, this takes me to this pair Fu and Fv. The addition over here takes me to Fu plus Fv. So much so. But if I say that these two are same, that means I am saying if you look into the composite, this composite is same as this composite. Right? Okay? So that's what preservation of this addition means. Okay? You can replace the whole idea by this nice little diagram. Okay? So this is the diagram for preservation of addition. We are going to see many such diagrams.
Preservation of class.
Bloemfontein, can you please mute your mic? Bloemfontein, can you please mute your mic?
Come again?
So this is the preservation of addition diagram. We will be seeing many such diagrams as we go along. Often diagrams help us to understand as mnemonics. Okay? So, what does this preservation mean? It precisely means that for any two vectors u and v that you might take from v, fu plus fv is f of u plus v. Oops. Do you get someone? This is what is meant by preservation of addition. Okay? Now let's see what do we mean by preservation of zero.
So
Yes.
if you have like say we defining a vector space like RGB, a color spectrum, 255, 255, 255, and I want to transform that to say monochrome, black and white. Is this the same thing like I'm transforming that one vector space to another vector space, RGB to monochrome, but I'm keeping the integrity of the vector?
Yes, you're keeping the integrity of the color distribution. Okay? So what is preservation of zero? Remember, I have a zero in V and a zero in W. So as simple as this, preservation should mean f of zero is zero. Right? As simple as this. Okay? The preservation of minus well, it should still be the same. If I take a V from V, then f of minus V must be minus of fV. We can look upon this by this diagram again. So remember, I have a function. Remember when you say that every vector has a unique negative, you're actually telling me a function. Okay? What is it doing? It is taking v to minus v. Alright? In fact, you are giving me a bijection there. Alright? Because if minus v is equal to minus w, you know v is equal to w. Right? And if you take any vector, v, it is minus of minus v. So it is surjective. Right? So you're giving me a bijection. So, v going to minus v is this side, and you have this function, so this f is taking me to f of minus v, this is going to f of v, so this is taking me to minus of fv. And what you are saying by this preservation is this diagram should complete. Okay?
In terms of preservation and closure, are they the same thing?
Closure is something which we don't require because we have said it's a function already. Right? What is the closure saying? For each pair of vectors u and v, there exists a vector called u plus v. A unique vector, but that's what I'm saying by defining a binary operation. Alright? Now, the last thing is preservation of the scalar multiplication. now seen these diagrams, it will be nice to draw the diagram first. So, we have the scalar multiplication here, and now what function do I give here? Well, I don't change my scalar, but change my V. So why not write this as 1 cross V, 1 cross F. So what is this function 1 cross F? Well, by 1 I made the identity over R. So what is this 1R cross F? So this is R cross V to R cross W. It is taking the pair XY. I'm applying identity of R on the first. So that doesn't change my X. And it changes my second coordinate to F over. Alright? So you see, you can go on creating functions just like this. Okay? So creating functions should not be.
Sorry.
Yes. Yes.
Yeah. Can I take you a bit back to 3, to the preservation of the inverse of V there?
Yes.
On the diagram, the preservation diagram.
Yes.
For instance, on that notation, when you are talking about from V to FV, just my question is, can you please explain that preservation diagram in terms of the flow, how you move from...
So what are you doing? When you say it about the inverse or the negative, you have given me a function from the vector space to itself, which is the negative, right? Which is this vertical line, V to V, V going to minus V, and W to W also, W going to minus W, right?
Yes.
Now, I have these horizontal lines already giving me those functions, F and S.
Yes.
So let's come to V. On the top, V is taken by F to F of V, and then vertically down it goes to minus of FV. Okay?
Yes.
Now, start again from V on the other side. First go down, you go to minus of V, and then F again takes me to F of minus V.
Okay.
So there are two outputs that I see over here. So the condition is demanding that these two outputs must be the same.
Okay.
So that's exactly the preservation of minus V.
Okay.
Yeah? So the condition is always about having these outputs same. Okay?
Yes.
So again in the scalar multiplication case, if I take a pair lambda and V, I come down to lambda times V by the scalar multiplication in V. Okay? Now, I go over here by this map to same lambda but F of V. Now the scalar multiplication takes me to lambda times F of V. Now this lambda times V is taken by F of lambda V. So the demand is to make these two equal. Okay? So that is what is meant by preservation of the scalar multiplication. Okay? So now we understand what we mean by preservation of addition. So let's go back. Preservation of addition is this equality. Okay? Preservation of 0 is this equality. Preservation of negatives is this equality. And preservation of scalar multiplication is this equality. Okay? Now, so our transformation that we suggested, we must look for a function which has all these equations. F of u plus v is f of u plus f of v, f of 0 must be 0, f of minus v must be minus of fv, and f of lambda times v must be lambda times fv. Okay? But in our special case, we are a little more lucky. These two, we will show now that these two get automatically satisfied. Okay? So that's what I'm going to show. So that's my T1 today. If be a function from the vector space such that which preserves, be a function which preserves the vector addition then it preserves the zero vector and the negative of a vector. That's what I do. So if it preserves addition, then it will preserve the zero as well as the negative. Yeah.
So which means if the first statement say
2 and 3 will be done. Okay? So that's how we come to the definition which says only number 1 and number 4. Okay? Alright, let's look into the proof. So given f of u plus v, this is fu plus fv for all okay. Now 0 plus 0. Yes, 0 is the identity. Right? There's nothing to worry about this. So this tells me f of 0 plus 0 is equal to f of 0. But f of 0 plus 0 by my preservation of addition is f0 plus f0. Yes? Now, if I add minus of f0.
Excuse me, sir.
Yes, yes.
Sorry, sir. Sorry, just on your proof. Now, when you say I just want to see what informs your logic from moving to say f of 0 plus 0 is equals to 0, f of 0 f of 0 plus f of 0 is equal to f of 0. What informs that logic? And I'm trying to think in, are you thinking in general terms of just general functions here, or?
No. Look into the first line. It says f of u plus v is fu plus fv. F is preserving addition. That's why.
Okay, that's fine. No, I get it. Yeah. Okay.
Yes. So now if I add minus of f0 to both sides, right? But then by associativity, I know that this will be equal to f0 plus this. So as using associativity, I get f0 is equal to 0. Right?
When the answer is number, explicitly saying we're using associativity.
Yes. Yes. And this one is okay? All right. So f preserves 0. Okay? Now let's see about further. For any u in I had v, right? F of 0, which is 0, I know. So this is f of v plus minus v, because 0 is v plus minus v. Now by my addition preservation, this is fv plus f of minus v. Okay? And so this implies f of minus v is minus of f. Okay? Adding minus of fv both sides, using associativity and so on. Okay? Alright? So it preserves the 0 and it preserves the negatives. Okay? So preservation of addition in this case tells us, just observe a little more. You see, this was nothing. In fact, I did prove something much more general. I say that suppose, and I leave this to you to check. Suppose I have a binary operation on V which is commutative and which is associative and has an identity. Okay? I take out even the commutativity, I didn't require it. Which has, so a binary operation on V, which is associative, has an identity, and every element has an inverse. Likewise for W, okay? And f is a function which preserves that binary operation. Alright? So f of u plus v is equal to fu plus fp. Then f preserves the identity and f preserves the inverse. Okay? That's the proof that I've given actually. Okay, so I just make a remark and I give it to you. So remark, there is a much more general statement about binary operations and inverse made here. You formulate and prove. I'm not saying that this will be required or this is examinable, but it is nice that you can see, okay, that this is the only thing. And what I will expect you, well, this is the learning. You should see slowly. You should try to get yourself focused. And while I'm proving, you should try and see what are the things exactly that is required in the proof. Okay? So even if I'm saying it in a much more special case, just by observing that, you come up with more general results for yourself. Okay? You can make that remark also in class. Okay? Do you require this? Do you require exactly this? Okay? So you have to observe what is exactly required to effect this proof. So I required a binary operation which is associative as an identity and has an inverse for every element. Then a function which preserves that binary operation will preserve the identity and inverse.
So about master definition.
Yes. And what is required? What exactly is required? Okay, that's the crux of, in fact, all of mathematics comes on. See, in mathematics we do not have, it's more like music. We have it's a game. We have certain actions and we prove things. Okay? So what is required is to know is what is it that I need to prove this. Okay? So that's the most important part of mathematical training. Alright. In fact, binary operations which are associative and has an identity with each element having an inverse makes a much more general structure which is called a group. Okay? So, alright. So, now we can formulate the definition of a linear transformation. From a vector space is a function which preserves the vector addition and okay? That's the linear transformation. So now you know how to check. How to check that this is a linear transformation? V and W must be vector spaces. Must. Okay? Otherwise, the notion of linear transformation doesn't make any sense. Okay? So, must preserve the addition. It must preserve the scalar multiplication. Okay? You know that B is enough to ensure that f of 0 is 0 and f of minus u is minus of fu. So you need not check that. Okay? You need not check that. But that gives me, so, you know what? The first attempts should not be in checking. The first attempt should be in throwing out. Just like government officials. Sorry. Okay, you go to an office, it doesn't want to work, so it finds out a way how not to work. Okay? So you're missing this application, you're missing this. Okay? So the moment you have this, the first thing what to do? Check f of 0. If f of 0 is not 0, it's not a linear transformation anymore. Gone. No checking. Right? So what do you do? The moment you have a function, first check whether the domain and the codomain are vector spaces. Okay? They are not, one of them is not, gone. Yeah.
So then if you give us a problem, we have two vectors, and then one is a vector space and the other one is not. Then how do you prove that? Is it necessary to state?
So that means that we already did, right? How to know that something is not a vector space. Yeah?
Is it necessary to prove all the points there?
So you immediately say that this is not a vector space. The domain of the codomain is not a vector space because ABC. So the question of checking over linear transformation doesn't arise anymore. Okay? So you see, this is how you cut down your computations. Yeah? So, that's the first thing. Well, both of them unfortunately is a vector space. Okay? Now the first thing to check is just try and see what is the value of f0. If f0 is not 0, gone. That cannot be out. That cannot be a linear transformation because you know every linear transformation does that. Okay, so this is like that government official attitude. You don't have this form B24A, right? So f0 is not 0. Okay? Well, unfortunately that also gets satisfied. Then check f of minus u. If that goes away, so you always first try and see the least path. Okay? So if you get a quick confirmation by few checks that this is not a linear transformation, you don't go through all these procedures. Right? But in the unfortunate case that you have all of them to be true, then you go in for B and C. Okay? Now B and C can still be, these two can still be condensed into one. So both of them imply and gets implied by another condition. Let me write it as D. And what is it? F of u plus lambda times V is Fu plus lambda times Fv. That's quite obvious, right? If you have B and C, f of u plus lambda times V would be f of u plus f of lambda times V from B. And if you have C, then it tells you lambda f of lambda V is lambda times Fv, right? So that's a single check. Okay? On the other hand, if you have this, if you take lambda to be 1, you have B, okay? And if you take u to be 0, you have this, right? So that's the whole idea, that you can replace it by a single check in D, but the steps are, first check whether V and W are vector spaces themselves, then Well, you grudgingly will try to check, but first check whether f0 is 0, no, goes out. F of minus u is minus of fu, no, goes out. If all these things are negated, that means V and W are vector spaces, f0 is 0, f of minus u is minus of fu, then you do this check B. Yeah.
So then if the first part, both the vectors, so both the sets are vectors, but then the f of 0 is 0, but then the last part where we say f of negative
is not satisfied. Yes. So then also it's not a vector space. It's not a linear transformation. Yes.
So which means all three must satisfy so that the following two should be
yes. So that means your computation procedure should be like this. You are given a problem. You first check whether the domain and the codomain are vector spaces. That is step one. Okay? Answer is yes. No?
Sorry, sir?
Say yes.
Sorry, sir? Now, what
Yes.
happens when that scalar is on both vectors? Can't you
When
get
the
a situation like that to come up with D? On D, you say that the scalar lambda it's only on V. But now, what happens when it's on both? What would be the situation?
Aha, yes. So that is also another equivalent formulation. So, f of lambda times u plus mu times v is obviously lambda times fu plus mu times fv. Okay? So, these are all equivalent formulations, but I find D to be the simplest. Okay? Alright. So, what would be your computational approach? You are given an arbitrary function between, whether it's a vector space transformation or linear transformation. First check, step one, whether both the codomain and the domain are vector spaces. If the answer is no, you stop immediately saying it's not a linear transformation. The answer is yes. So then you check whether f of 0 is 0. If the answer is no, it's not a linear transformation. Yes, check how f of minus u is minus of fu. Okay? Sometimes you can find out a very quick, looking into the function, you can possibly find out a very quick way to see, oh no, minus is not satisfied. Yeah? So then you know, gone. It's not a linear transformation. But if it is still that, then you use D. F of u plus lambda v is equal to fu plus, right? And then you come up. So I'll give you examples to show that this computation principle is. So for instance, let's look into examples now. First, yes or no? Yes, it is. Okay? It is. Right? 2